Imagine a hotel with infinitely many rooms, each numbered 1, 2, 3, and so on forever. Every room is occupied. In the real world, this means no more guests can be accommodated. But this is no ordinary hotel. This is Hilbert's hotel, where the rules of infinity apply. When a new guest arrives, the manager simply asks every current guest to move from room n to room n+1. That is, the person in room 1 moves to room 2, the person in room 2 moves to room 3, and so on. Now, room 1 is free, and the new guest checks in. Problem solved. But what if a bus carrying infinitely many new guests arrives? The manager moves every current guest to room 2n. The person in room 1 moves to room 2, the person in room 2 moves to room 4, and so on, freeing all the odd-numbered rooms. So the new set of people can fit into the odd rooms. Suddenly, there's room for every single new guest. This paradox shows that infinite sets can be rearranged to fit more elements without ever running out of space. Infinity is not like any number you know, it's limitless in a way that defies intuition. Next is Galileo's paradox. Galileo observed something curious about numbers. Consider the set of natural numbers 1, 2, 3, 4, and so on. Now consider the set of perfect squares. 1, 4, 9, 16, and so on. At first, it seems there should be fewer squares because most numbers are not perfect squares. Yet, there is a perfect 1-to-1 correspondence between the two sets. Every natural number n pairs uniquely with its square and squared. This means the set of squares is just as large as the set of all numbers, even though it is only a part of it. In the world of infinity, a part can be as big as the whole. This paradox reveals that size, when applied to infinite sets, doesn't work the way we expect. Next is Zeno's paradox. Zeno of Ella, an ancient Greek philosopher, proposed several paradoxes about motion. One of the most famous is Achilles and the tortoise. Imagine Achilles, the fastest man, racing a tortoise that starts with a head start. Zeno argued that Achilles can never overtake the tortoise because he must first reach the spot where the tortoise began, but by then, the tortoise has moved ahead. He repeats this reasoning infinitely, every time Achilles reaches the tortoise's last position. The tortoise has moved a little further. It seems Achilles must take infinitely many steps. So he never overtakes the tortoise. But modern mathematics resolves this. The infinite series of distances, 1/2 plus 1/4 plus 1/8, and so on, converges to a finite value. So Achilles does catch up. Still, Zeno's paradox highlights how infinite divisions of time can be deeply counterintuitive. Next is Thomson's lamp paradox. Imagine a lamp that is switched on and off, in intervals that get shorter and shorter. On at 1 minute, off at 30 seconds, on at 15 seconds, and so forth. After 2 minutes, you've flipped the switch infinitely many times. So, is the lamp on or off at the 2-minute mark? Both answers seem possible, and yet neither fully makes sense. The paradox arises because an infinite number of actions in a finite amount of time creates a situation where the lamp's final state is undefined. It's a perfect example of how infinity challenges our understanding of cause and effect. Here comes the final paradox for today. Imagine you have an infinite number of $1 bills. Now imagine someone else has an infinite number of $100 bills. Who is richer? Leave your thoughts in the comments below. I'd love to hear your take on this one. Thank you for watching. If you enjoyed this journey through the strange world of infinity, make sure to like, share, and subscribe for more mind-bending explorations. Until next time, keep thinking infinitely.